But there are other subspaces that don't really reside in n space. And the reason for that is because vector spaces are not confined to just those subspaces or subsets of n space. You know, we know by now that we can create vector spaces out of certain types of matrices, certain types of n tuples, certain types of functions, and a variety of things. So I'd like to just give you some variety of, some of the other standard types of subspaces, what the notation for them is, and include some examples of functions that you might see in these types of subspaces. The first of the vector subspaces is capital F, and interval notation for all real numbers. And this is a notation used for the subspace consisting of the set of all functions that have a domain of all real numbers. So to give you some examples, f of all real numbers, it is a set, and I'm going to jot down examples of functions that have a domain of all real numbers. Sine x would belong in this set that has a domain of all real numbers. It is also a function. E to the x meets the criterion. It's a function and defined on all real numbers. Polynomials definitely belong in this set. Every polynomial is continuous and has a domain of all real numbers. So something as basic as x plus 3 would be an example of a function that resides in the set. And there are many, many more, actually. This happens to be the largest of the subspaces involving functions. A subset of f of all real numbers would be capital C of all real numbers. That's notation for the set of all continuous functions that have a domain of all real numbers. Let me give you some examples of functions that would be in here. Certainly sine x is continuous and has a domain of all real numbers, so sine x would belong in this set as well. So would e to the x, so would x plus 3, so would some of your other polynomials, such as x squared minus 4. Cosine belongs in here as well, and many, many more. And you might be wondering, like, what is the difference between, capital F and the capital C sets? I'm going to show you a couple of examples, in which case we have functions that are defined on all real numbers, but are not continuous. So I'm going to go back up to the first row here, and an example of a function that has a domain of all real numbers, but is not continuous, would be something called the greatest integer function. Has anybody ever worked with this type of function before? This is sometimes referred to as the staircase function. But the notation is officially for the function that's called the greatest integer function. This does have a domain of all real numbers, but it consists of a bunch of little line segments that kind of, increase in height as you go from left to right. It really resembles a staircase, which is why it's often referred to as a staircase function. Also in this set would be some piecewise defined functions, such as maybe f of x equals And you've probably worked with piecewise defined functions before. I'm going to just create a random one here. Piecewise defined function with two rules. We'll say x squared plus 1 if x is greater than or equal to 0, and 3x minus 2 when x is less than 0. This would consist of two pieces of a graph that are disconnected, but it would still have a domain of all real numbers. So these two functions belong in the set capital F, but would not belong in the set C because they're not continuous. And then one more that I want to include in here, and this is for you guys to look up when you get some time. Very, very interesting function. It's defined as a piecewise function, but the rules that it consists of are just two numbers, two values. One rule is use the number 1, whereas the other rule is use the number 0. And you use the value of 1 if x is rational. So if x is a rational number, such as 2/3 or 1/2, the function takes on the value of 1. Whereas if x is irrational, such as pi, the value of the function is 0. This actually is a function with a domain of all real numbers, and it's not continuous. So it would belong in F, but not C. And the name of this function, in case you guys are interested in looking it up, is called the Dirichlet function. And no, I did not swear or sneeze. Dirichlet function. It's a pretty neat, but albeit a little awkward function. I remember having to work with this in some of my graduate level courses, and it was a pain in the arse. But the history of it and how it came about and everything like that is still pretty interesting, nevertheless. So I don't know. Like I said, if you get some time, you might want to check it out. It might fascinate you, or not. So that takes us to subsets that are within C of all real numbers, which would be C bracket A, comma B bracket. And this consists of the set of all continuous functions that are defined on a closed interval of the x-axis. And so this allows for graphs like, or functions such as tangent, square roots, rational functions, maybe logarithmic functions. So I'll give you some examples here. I want to look at the set of all continuous functions that are defined on the interval 0.5, comma 1.5. Okay, so specific values of a and b. Tangent would actually belong in the set. Now, tangent's not continuous on all real numbers, so it doesn't belong in the set above this one, but it is continuous on certain intervals of the x-axis. So I'm going to put tangent x in here. Another function that is continuous on this interval would be the square root of x, as well as the natural log of x, and many more examples would exist. So sets like these allow for some of those functions that wouldn't ordinarily have a domain of all real numbers to become continuous here. Capital P sub n consists of the set of all polynomials of degree n or less. So as a specific example, if we had capital P and n was the value of 2, this would consist of the set of all polynomials with degree 2 or less. So one such polynomial that you would see in the set would be something like 3x squared plus 5x plus 1. Is it possible to have a function in here or a polynomial in here that would be something like x minus 10? Could a polynomial like this belong in the set P sub 2? Yep, definitely. Keywords here, degree n or less. So as long as the degree of the polynomial is 2 or less, it would belong in the set. Obviously, this has a degree of 1, so it would belong in here. You would never see any polynomials with x cubes in here, or x to the 4th, or x to the 5th, and so on. Just to give you some variety, even your constant functions, such as 7, would belong in this set, right? And many, many more polynomials belong in P sub 2. Certain subsets of m by n matrices form subspaces. So here we're seeing a second instance of capital M with some subscripts. And we worked with a set yesterday, M sub 2, 2, which consisted of the set of all matrices that have size 2 by 2. In general, M sub Mn is defined as the set of all M by n matrices. Now, M sub Mn in and of itself might not be a vector space, but under certain conditions on these matrices, we will be able to form subspaces. So I'll give you an example of some matrices that might be in M sub 2, 2. Okay, M sub 2, 2 consists of matrices that have a size of 2 by 2. So, we definitely would have the identity in here. Okay, we'd have the 2 by 2 0 matrix, and basically any other 2 by 2 matrix would belong in the set M sub 2, 2. I'll just say A, B, C, D. Now, depending on what operation we're working with, the operation of addition and scalar multiplication, M sub 2, 2 might not form a subspace, or it might. It just kind of depends on the operation of addition and operation of scalar multiplication. And those will be fleshed out for us. They'll tell us how they want us to add and scalar multiply. And based on the form of the matrix that they provide us with and those operations, it's likely to form a subspace or not. It just kind of depends. But these are some of the more popular subspaces that don't revolve around n space that we'll come across from here on out. Do you have any questions for me?